a question that I think that your use of the phrase observed statistics is not the usual definition, right? Because you actually have theta in it. Is that so? What do you mean by the observed statistics when you have a unknown theta in it?
Oh yeah, then it's a statistics. Then you probably don't want theta. I just put it here. So it's a data. It's mapped to a model. So it's D in your observation.
But the theta itself is not entirely observed, right?
D is the data. I just mean data. There's nothing
to
D is the data. Okay. But I will tell you later, you will see what this data is.
Okay.
In many cases, it's transformed in some sense in physics, but these data in general.
Okay.
So, I mean, in astronomy, I mean, effectively, I guess, d of theta is what we would use as chi-square or c-stat.
Sure, sure.
So that's like
a transformed.
That's like a statistics, not observed statistic, but it's
well, so the chi-square involves both the data and
model parameters,
and which makes it includes the theta.
So if you observe the other one from a model, I guess, then data are from simulated. I think that's the difference, right?
Can be neural network, can be other anything.
So it's like a DM is like an emulator.
DM is a model, can be a physics model as well. Yeah, it can be a PDE,
Okay.
and other thing. But these I'm just talking about general framework. This is not what I will advocate. That many people do it in physics, also in machine learning. You just do it. They estimate parameter by minimizing certain loss. Right. Okay. So there could be lots of this very useful and helpful. Could be a few limitations because you need to choose the loss and statistic. They may not be optimal, although they could be very sensible, like L2 loss, L1 loss. And if you start from here, you could have not direct natural uncertainty quantification, like interval. And then you could have lots of parameters, like in a neural network, you could have scalability and stability optimization. And in some scenario, you probably implicitly choose the data, like if you do a PCA, you may choose the dimension. In a neural network, you may specify how many neuron layer. So that, in some sense, people still will build in their choice of the approach. Now, let me just, why is not showing? Let me keep showing this. It's not. Okay, so then maybe I will quickly talk about the important things. Go ahead. Okay, so just one. The most important thing comes from the beginning. So I will introduce a two-step approach to improve this loss minimization. So we have a food here. Maybe I will just.
Now you'll be competing with food, you know.
They delivered somebody else's order and then had to return with our order.
Someone else then will.
We should have just kept.
It's all right.
It's okay. Yeah, so I will keep talking. So we propose to improve this into a two-step approach. So basically, we want to first build a large, I will explain the large later, a probabilistic model of untransformed data, started from the beginning. With parameter, even is large, with parameter that still can be identified from data. And I will show the equivalence between its loss minimization and the statistical estimator we know before. And then if it is not optimal in statistical sense, then we'll derive a more efficient estimator by marginalizing out the component. And I also want to highlight fast algorithm can be developed to accelerate this computation. And then we define this approach that define generative model and propagate the uncertainty from the beginning, data processing. We call it ab initio uncertainty quantification. Please, ab initio should not be confused with the first principle computation in physics, although they share some similarity that both sort of have the meaning from the beginning. So these are the paper we just submitted last week, and it was sent out to review from Physical Review X.
Well, it has a nice AI abbreviation.
So people do ask what is AI, and in this talk, it's ab initio. Okay, oh, good. I finished the first slide. For some reason I cannot move to the next page. Okay, good. Let me just slow. So, oh, you didn't see this page. Oh, I skipped so many pages. So I sort of get some promise I won't get punished if I don't talk too much on astronomy. I'll talk about imaging and statistics.
Yeah, please.
So we'll talk about signal, and we'll talk about scattering. I will introduce a technique in scattering analysis of dynamic, widely used tool in microscopy these days. And then I will talk about some generalization of this tool, like in PCA, not really, well, it's an extension of this principle about PCA, generalized PCA, and dynamic mode decomposition about some Kuhlmann operator. And we'll also talk about geophysics model of satellite interferograms. And surely you may kind of see this, the last two is calibration on imperfect model, and also imperfect modeling calibration by imperfect data. So that might interest to you because you know data quality is so important. Yeah. Okay, so let me get started. Let's talk about images. So I'm showing you two images. It's actually an image of a video microscopy. One is polyethylene. This is one type of widely used tracer or probe. People put this fluorescent probe to test the property of this material. And then the second is fibroblast. It's a connecting tissue of human and animal. And then we do this experiment, we'll put some substrate to guide this fibroblasts to align. This is so important to see how they align. I can show a video. This paper is recently published in PRX Live by myself and a collaborator. So let me, it's kind of hard to and show you this video. Maybe show you, see, this is the data. So let me say, this is one small image, field of view. We stitch like 50 of it, so we have lots of data. So I sort of show you, so you can see how they move this thing. Yes.
So what are, when you say data, what is it that we're seeing exactly?
I
mean, is this intensity of some of X-rays going through, or what?
This is optical light microscopy, just regular microscopy video. It's you do image. So you put a sample, small sample, and then you image them. So
how do you move it if it's?
They take a video.
It's a slice and.
Oh no, this is live. The cell move. So okay. So these are there are two types of movement we typically study. This is so-called like active matter. So they are alive. They move like a particle. They move self-perpetuate. So they start. So this we want to test. So they start from a phase that's kind of like disorder. And then gradually they become ordered because we put some aligned substrate to affect their movement. So that's what we want to study. So, but what you see here is the cell. Each of this red is one cell, and the blue one is its nuclei.
Like suspended in fluid or something. I mean,
oh, they are not on the fluid. Yeah, it's on some hard substrate. It's on a substrate. Can you repeat? Oh, the question is, what do we see here? Okay, I will repeat the question if I heard it. Sorry about that. So the question is, what do we see? So this is the optical light microscopy. It's imaging the what cell move. Each frame you see oh, actually this is very slow. So it spans 2 days. Each is 30 minutes. Usually we have this 0.0 something seconds for like thermal fluctuation. Cell move very slowly. So this is 2 days video, around 1.5 to 2 days. So we are seeing how.
I mean, is it
on substrate? No, not substrate. On hard substrate, liquid crystal substrate. It's not on a fluid.
Okay, I have zero knowledge of biology. So
similar to you. I learned from collaborator. I'm a statistician. But I try my best to explain.
Just think about this star. So the star.
Yeah, that's what I was trying to.
It's like a star. The first tool I will talk about is the kind of originate from star. But yes, this is one type of thing we will be talking about. Okay, now I can focus. And then one tool we'll see is this. So you how people analyze the dynamic, how they move is they localize the particle intensity by fitting some Gaussian profile. and do some filtering the noise, a broadband filter, and then you link particle. So you sort of need to say the next frame where this particle move, right? So you have quite a bit tuning parameter in this tool. You need to choose how large the size of insertion radius. You need to choose how large a particle is. You need to be tuned case by case. Even you tune those parameters, it could have very poor quality for optically dense system. You have lots of particles that may be not very uncommon, because for those things, you put those things into some like fluid, microfluidics. When it's very not viscous like water, you need small particle. Small particle, then it become, otherwise it will drop to the underneath, it will not flow there.
So
Yeah.
Is it opaque, meaning?
You could also have bleaching, or you could bleaching, so the fluorescent just become like dark. That could also be a problem.
So it's absorbed as you go from bottom to top.
Oh, if it is, we need to make the is floating, so we can test the thermal fluctuation. If it come to the downside, then it does not move. If it does not move, then we can't tell that, for example, hydrogel, the property of that hydrogel, how stiff it. I will show you one equation how to do that. But yeah, so it has many limitations. It does not have for non-spherical object. It's also not that good. If you move very fast, it could link to particle is very hard. Some system you cannot place this probe, so it's also not quite feasible. Yes.
So what exactly is the problem? So you have this.
Oh yeah. So we want to study what this process like. Is it, for example, thermal fluctuation? Is a Brownian motion? Is it O'Hahn-Wurldenberg process? Is a certain dynamic? I will show you the parameter. So in just one slide.
Okay, so you want to model the intensity.
Dynamic. I will want to model intensity exactly. Yeah. So second approach is the basis decomposition. I will talk about the Fourier one. So we don't need to track individual particle of these two. So let me just give some physics notation. Let's talk about ideal scenario first. In ideal scenario, each particle is like a point mass. It's like, let's denote the particle as xm, the m's particle at time t, and you do a Fourier transformation. You map this Cartesian space, original space, to Q, this reciprocal space. So this is 2D, so Q is Q1 to Q2, each is 0 to 2 pi. And then let's just define a property called perc. It's sort of you do a Fourier transformation, you add them up, you normalize them. And then let's define one of the most important quantity in this talk is called intermediate scattering function. Well, not in this talk, half of the talk is the intermediate scattering function that's defined in scattering, dynamics like scattering and other scattering of dynamics. It's a covariance of this perc and its complex conjugate. Covariance of this and lag time. Okay? So when it have very weak interaction, no interaction, which is usually assumed in microreology, you have this formula. I'm going to show you just you have.
I'm just trying to understand better. So
Yeah.
T here refers to the
time frame.
So this is more like you're studying. It's almost like autocorrelation.
Yes.
I'll call it that. But where is the spatial correlation?
It reconstructed by the Fourier basis. So I will show, for example, this, right? Let me just talk about this parametric model. Parametric model, for example, diffusive process like Brownian motion, right? One can show this is closed form. You can show after you transform into the Fourier domain, you can show this is you have this form, this FQT. So this is exact, this one. For other like O'Hahn-Wurldenberg process, we will show next in the simulation study, they all have closed form, but it's approximation. This one is exact. So that's you can map this information to this FQ. So this answer your question, what we are trying to learn is, for example, if you model by Brownian motion, then it's theta. So then why this theta, this diffusion coefficient is important. This theta, if it is simple diffusion, it can be related by the Stokes-Einstein. One thing is, this is for astronomy. Actually, many of these tools, for example, particle tracking, this tool, I've already showed you this Crocker's algorithm, originate from astronomy, some of these tracking tools. And if you want to name one, at least one person who have performed impact on as in astronomy and those tiny things, this Brownian motion thing is Einstein. Because when people do this force and try to model it by force, in this he already start to model this probability of displacement. So this is very nice. So oh yeah, is there a question, or you can unmute yourself?
Yeah, sorry to interrupt. I guess I'm just waking up and a little slow. Your equation here, it's a spatial, it looks like kind of a mixture of spatial and temporal Fourier transforming. I'm a little puzzled by what it actually means. And more to the point, it looks like it's a second order statistic. It ignores phase information. Is that correct?
Let me first answer the first question. This is ideal scenario. Next, I will talk about, we'll do 2D spatial discrete Fourier transformation, 2D, and then compute by FFT. So it's a spatial Fourier. You can think each image will do a Fourier transformation. I will talk about the tool. You will see what Fourier is. So it's spatial Fourier transformation at each time. Okay, that's the first question. The second question is second order statistics. So this is defined by this covariance. So you can think it is second order. Indeed, the only closed form thing I find is the diffusive process. All other are approximation by cumulant. This is I will talk about how they quickly tell you what they approximate. It's actually this FQT. You can relate it to mean square displacement, and then this mean square displacement, you define process, you can compute the mean square displacement, and this is by cumulant theorem. They are actually pretty good for many process. And then there's a thing I will talk about, this dynamic light scattering, and then this is the standard, this cumulant theorem approximation, second order, sure. And then
okay, great, thanks for clarifying. So at this point, you've discarded phase information, Fourier phase information.
Yeah,
correct?
Yeah, I guess so. Yeah, but let me maybe finish this. So from this theta diffusion coefficient, if it's simple diffusion, this can be related to a few things. So this KB is Boltzmann constant, T is the absolute temperature, eta is how viscous it is, R is the particle size. So in like dynamic light scattering is so commercialized tool. So if you know the fluid, how viscous it is, and you can test the particle size like protein size. So this is like gold standard on that field, like dynamic light scattering that they use. Or in another way, if you know the probe size, radius of it, you can test the viscosity of it. And then if you start from this one, if it's not like this diffusive, you can start from mean square displacement, and then you can get the storage and loss modulus by generalized Storch-Einstein. That sort of intuitively is like how elastic the material is, this kind of thing. Okay, then let me talk about, I cannot move this, let me, yeah.
So the eta and the R are measurement quantities, sorry.
Yeah, eta.
Quantities that if you change the method of measurement.
Yeah, they will all different. Okay. Yeah, it will change. It depends on the fluid, the material you put. Is a gel or something, water, then we know what it is. Good question. Yeah, so let me just talk about this physics tool first. This physics tool called the differential dynamic microscopy is a tool that you don't need to track particle. They do something like this. So this is the intensity, each intensity on X and T plus delta T. They look at the difference for each delta T, and then they do 2D spatial Fourier transformation. Okay, and then they average them. So this average, so this is a mix of statistics and physics coming. Yes. How exactly I define intensity?
So is it just the proportion of particles?
No, it's from the lighting. So it's a 0 to 255 for regular. It's an image like your phone. It's a light microscopy. It's not the. So this is a way to look at images by use of Fourier scattering type of way to analyze. But it's like your image. Okay. So okay. So let me. So here for physicists, it's just like a bracket and then average ensemble on T. t. Okay, so here in for statistician is like a mean over t, and then you define this. This is a square of this quantity, and then to average, and then this is the data. So you ask this question. What was the data here? It's this d.
What is the n then? What is it?
N is the number of time point. So it's a time point. How many time frame? And then in this quantity, people model it by this. So I will give you why they model it by this. But AQ is like a fitting parameter, and F is the previous F we just discussed. And B is a random quantity. You have mean B bar. Okay, and then they're gonna fit. So they call this thing image structure function. And then for example, if you assume Brownian motion, if you're OU, or like other like mixture, like fractional Brownian motion, then you can fit. Then how do they fit? They have all these parameter. They have this parameter, this theta, A and B. And then the thing is, at each range, if it's isotropic, at each range, you have one of this A. So you have actually lots of parameters. They are typically in physics, there are two ways. One way is just treating theta also differ by each J. For each wave vector, you fit one set of parameter and then you average. Okay, minimizing some L2 loss. That's one way many papers in physics do. Second, you use some good estimate to have a little bias for A and B, and then you B bar, and then you estimate theta. You plug in those estimator and estimate theta. Okay, and then in both ways, you cannot use all. You have to specify a wave vector like scattering. You have to choose a wave vector. It differs case by case. Okay, and then let me say you have a wide application like in material. For mostly like MPT does not work that well, right? For example, non-spherical object, like colloid gel, and those protein inside the cell, like actin microtubule network, etc. This is a very great, it's a really good work because it treats each pixel in your image like a point detector in dynamic light scattering, which is so widely used. So it brings a lot more information than this dynamic light scattering. It does not need to tune any parameter to track individual particle. Yes.
So on the last slide, you were fitting data as well as
Yes.
A and B.
Yes.
On slide before, you talked about a non-parametric fit where theta can also determine
Yes.
delta T.
Yes.
So actually, this is a many-dimensional problem where you have different Q and different delta T.
Yeah. Very good. So there are two types of approach. One is you could assume it's a model, then just one parameter for theta, or two or three or four, or you can go this, I'll show both. And this is a lot larger. You are very right. It's much harder. Much harder. And this is a model-free approach. You don't need to specify a model. Very good question. Okay. So that's what they do. And then there are three challenges. One challenge is specify wave vector. I think it is not uncommon in physics. In many Fourier-based tools, you have to specify certain wave vector range. And it depends on expertise, and move to another system, you need to change. So this is harder to make it automated and do a high throughput experiment. And it could have a lack of quantity.
Is that range of vectors, do you mean?
Q, the range, how many range in this case, like in your, right? So it's on Fourier space.
Okay, so
yeah.
the wave
Number of wave vector.
Yeah.
Frequency, how many frequency you have? They tell different thing actually. So what you see here, for example, this is, I'm showing DQT. Each curve is 1Q. They drastically different because of AQ is very different. And then you want to average them. For example, this is like, this is on specific delta T. We use that theorem to directly invert. There are approaches to this, directly invert to get MSD at specific delta T. And you see a larger Q, it tell you if you average, it will be something like this. A large Q may be something like this. If you specify specific range, it may be true. You maybe get close to true. And this is just simple Brownian motion. Okay, so you have to specify a certain range. No, then a question need to be answered is can we not select in the range? Use all. Can you? What is the question need to be answered is what is the model that for this real space probability model for this real space image intensity? Okay, so I guess that's the question I pose here. Okay, so then let me just build a model. So this model may not be so familiar with you, but it will be related to something you might have heard before. It's not exactly the same like that. It's like PCA or latent factor model, but it's a very physics encoded latent factor model. So here this W, so let me just denote this Y is the intensity on n pixel and at a specific time frame. And then square image, then is n1, n2, n1 square root of n. We can still deal with the rectangle and other images, but let me just make it easy. And then this is W prime, the W star, this is the complex conjugate of 2D discrete Fourier basis. And then this epsilon is normal distribution with this variance b bar divided by 2. And latent factor is a process, it's a complex latent factor. It's split into two parts, Z real and Z imaginary. Each is n-dimensional Gaussian vector. And it's Z at each J, each that Fourier transform that pixel at all time frame is a multivariate normal with a specific correlation matrix. So AJ is a perverse AJ. This correlation matrix here, the key is coded by this F. This F comes here. So this F codes each principle of diagonal that's coded by the previous thing we introduced, that intermediate scattering function well known in physics. But this is a new model. I built this model, and then you may ask, why do we care this model? And then let me just show you one thing. So this is a connection between the previous physics approach and this. So if look at the right-hand side, that's the model, that DM thing. So it's AQ, right, this thing. Okay, show if you start from that model, right, if you look at that Fourier transform quantity and look at the difference, you can see this quantity, we can show it, this quantity that equal to this. And then this quantity, what it is, if you stare at it, anyone, what is this quantity? If you are stats or spatial stats, or you stare at this quantity, looks something familiar. Of course, this I should define this complex conjugate though. So this is Fourier transformed. So I basically look here. I basically use W times the previous one square root of n and get this y hat, and then at each q they have one of this, and then I basically define this quantity and do expectation. So this thing is the temporal variogram, and it's in the reciprocal space, in the wave vector space. So this temporal variogram, so in statistics, the spatial variogram is well studied long time ago, 30 years ago, actually almost 40 years ago, by many other people. For example, one is Professor Nora Cressy on famous paper on this fitting variogram model by something. So you need to do something. It's not L2, it's not easy way you can solve the problem. The reason is here is even harder. The reason is AQ is very, very different, as you see in the previous one. It's very different, and then you need to weigh them. And then at each delta t, they are correlated. When you have correlation, weigh them is not that easy. So if you directly start from here and then fit this stuff, it's hard. Of course, if you specify a certain range, it may be close to the literature value, you will see, but you know, it's not easy. So so summary is DDM, the previous tool, is fitting variogram.
So this variogram is something that people do usually
In statistics?
Now
I think it's more on exploratory data analysis. 30, 40 years ago, people fit. I'll talk about more efficient estimator. This is not the most efficient. And it's just, it's hard. Spatial is not that hard because spatial, the scale may be the same. Here it's much harder. The scale on each Q is very different. I just show you the curve. AQ can be 10 to the fifth, and can be 10 for different Q. So it's hard if you directly start from here. And that's the current practice in this type of tool in physics. Okay, so do we have a better approach? So I build this model, and then I write down this connection, and then you may think that's probably start with statistics. So here I basically integrate all Z, and I can show it's a product of multivariate normal. And then this sigma J is here. So you have this form, and this R, remember, is coded by that intermediate scattering function. Physics model comes here. So Basically, we want to do maximum IQ estimator, maximum marginal IQ estimator. We integrate all Z, and here one thing is we did use the unbiased estimator for A. We can show it's an unbiased estimator for any B bar, because for physics model that can reduce a lot of dimension. Because for example, if you assume Brownian motion, they become 2D. 2D optimization, you can use like BFGS or other Newton algorithm. That's pretty good, right? That's MLE, but then I will talk about the computation, because this issue is over time, it could be very slow. You need to invert lots of covariance, and then they are different on each ring. So then before I talk about the computation, this is on the anisotropy process. We can extend to anisotropy process if you have the particle move on certain direction. For example, it's confined in one direction. That's for our cell. It sort of follow our guidance, it move more on the horizontal direction. This can still be done. We can show in one step of our proof, this can be related to something like this, and then you can model two direction, for example, on different set of parameters. That's still fun. Okay. One thing is this AJ, actually, this depends on how the shape of the particle. This AJ does not depend on the dynamics. Okay. And let's talk about generalized Shu, right? So for video microscopy, this typically taken equally spaced in time. So if you directly invert it, and you need to do optimization, you probably need 100 iteration, and then you need invert many covariance matrix. It can be as long as it can be 10 to the 15. It can take months in desktop. Just for regular video, like 500 by 500 by 500, we can deal with different size, like times 1,000 times 1,000 times 4. That's fine. But even this, they take this long. And then you can actually use this generalized Shu algorithm. So this is a topless matrix. There's a topless matrix is a general version of circular matrix, and each principal diagonal, like first principal, second principal, they have the same. They are the same. So it's a specific matrix, equally spaced in time. They all have this form, and then you have this well, this is a typo. This is the inverse. The inverse can be written as these two quantity, the subtraction, and then they are lower. Each of these is a lower topless matrix, and then the determinant can also be written as this way. All the coefficient can be solved iteratively by solving this generalized Shu algorithm, like a Shu polynomial. It can reduce the computation from n to the third to this number. This is pseudo-linear, so linear to the number of time points. There's no approximation. And in R, there's a package called SuperGauss. It is from thesis by Lin Yun. Why I really want to talk about this talk in Harvard, because this is also related to Harvard. Yunling is actually a PhD student from Waterloo. His advisor is Martin Lissy, who actually I think graduated from Harvard before. So this package he had. We do more on the common futures kind of thing, but this is also new to us, like a year ago, and we're happy to find this, and then we learn this. But the method is actually Shu algorithm, like in the 80s. And then this can deal with any n. Okay, their contribution and implement these very nice packages. And then one can further reduce data. So this reduced for this thing, reduced like 10 to the 4th already, no approximation at all. You can compute like exactly. And then this, you can further reduce the dimension by selecting the first J0, because the larger frequency, it behaves like noise, more like a noise. I will show you both, like using aiUQ or subset. It typically doesn't matter too much. Estimate noise matter, but estimate the physical parameters doesn't matter too much. But for very slow dynamic, you need to use more. But usually 99.9, we use this kind of thing. Look, the larger ring have more data, and they behave like noise. So if you use 25%, it sort of reduce 15 to 16 computation already. So it's good. So we can reduce like 10 to the 5th times with nearly no approximation. Okay, so that's implemented.
Sorry, you have
yeah.
to choose that if you're already knowing that those modes are necessary, or
No.
record.
I show you here. So I use aiUQ. I can use aiUQ, no problem. All of the Q, there's no problem, and I can reduce. Use just a 50, let's say 25% or 50%. Explain how many A. You summing up all this A and divide it to see how does it explain 99%, 99.9 is like a PCA. The reason is high frequency behave like noise. Okay. All right. So this is showing if you use DDM, you have to choose it. It's you have to choose wave vector in this approach because in maximum likelihood, marginal likelihood, we naturally weight information at each wave vector. You don't need to select the wave vector anymore. So see here is a different fraction of Q, your estimated truth. And then this is the marginal likelihood for the all Q actually. And then this is our estimated overlap. I will show many more simulation. All right. And there are more because we define this data generating model or generating model. You have uncertainty. Here it's actually a little tricky in physics. So the information actually comes from this number of parts. So there are two sets of uncertainty. One is parameter estimation, right? It's a stochastic system. You have uncertainty from parameter estimation. Yeah, usually three-way in statistics. You do when you don't have closed form, there's Bayesian. You compute the posterior. Usually you need to sampling, or you do asymptotic approximation like CLT. This is following an increasing domain, ELT, or you do bootstrap. Usually these three. For this problem, we try three. They are similar. This is the fastest. And then there's the tricky part. I think statistics is a kind of unconventional. Is if you think about it, how many data do you have? Of course, it's correlated. So it's not, if you think about effective sample size, it's correlated, it's not that large. But even you think about, you take that into account because it's in our model, the information actually not come from n number of pixels. It comes from n number of particles, like 50 to 100 in each frame. So you may want to discount the likelihood like times this power because that's the information. You only have like 50 time series, not 10 to the 5th time series. So that will actually do that, actually behave pretty well. Yeah.
You mentioned this, so your asymptotics here is you're assuming the region is increasing?
Good question. Time. In physics, there are two different types of ensemble, but here is a time increase. We say the time is large. Physics usually is
not like you have higher frequencies within a fixed time.
No, it's just you take a longer imaging, longer video, like that's more. And another type of asymptotic is to put more particle, infinite particle.
Right.
That both are fine for this case, as long as they don't interact too much. Right. So
if you observe longer period, is there any you still assume it's the same region, the stationary still holds, so.
Oh yeah, good question. A good question. So up to the that's actually a very good question. If I assume this model, then it's just that kind of model, like Brownian motion, that doesn't matter. If it's I start from the approximation, right? That's also assume kind of stationary because anything you talk about mean square displacement, if it's changing over time, that's not well defined as mean square displacement because it's defined on lag time. If it also depends on time, keep changing, then it's something else we need to think about.
But the real problem itself, is that assumption reasonable? Saying it's not changing, it's there.
That's a good question. Yeah, I think it depends. But for many thermodynamic processes, if you have a model that usually is captured by that model, it's a parametric model, then you already defined the entire to the time to the limit. So that should be fine. But
that's by the model itself.
By the model, sure.
For model, yes. I'm asking like for the real.
Sure.
Real data.
No, in that PRX life, no. So there are two things. One is the cell, you have more and more cells, they keep growing, it gets slower and slower. This dynamic. Right. No, let me say it's no. And yeah, anyway, let me know. Yes, that's a good question. But anyway, for many thermodynamics, we want to test hydrogel, they all hold. The second is discretization pixel. This I don't want to talk too much. As long as you have 500 by 500, it's almost zero. It's very small compared to with the first one. Then you can do model selection, like use any like information criteria. There are approximation of like base factor. You can use AIC, or you can calculate the predicted error. You predict next time frames, save time, some frame, you can do it. Because of you have a generating model, all this become true. Before this, I don't think it's quite, quantified, in physics, how to select model. People just use their knowledge. They don't really give you the interval of the estimation. Okay, I probably will quickly just show you. These are some of the model in simulation. We have large and small video and We simulate 6 processes. I didn't make them myself. These are all in physics, like fractional Brownian motion is like diffusion, it's sub and super diffusion. And then it's OU, it's also in physics. And then the mean square displacement of this is same as a continuous time random walk, like in anomalous diffusion. They are widely used. A mixture of FB and OU is like noisy continuous time random walk. So this form are familiar with physics. Actually, we just test them, and then I will also show you the model free. That's also not in our submitted paper, which got that a few weeks ago. But anyway, show you for example, this regular video, small video actually are also good. Regular video, let me just show you this true parameter, estimate parameter, the interval. They're all good, almost exactly identical. All this thing, and I cover it. And then mean square displacement, they actually all this overlap. Our approach either selected Q or reduced Q much better than the DDM approach. DDM, you need to assume certain wave range that differ process by process. And then we also show MPT. MPT, you see the longer time you have less information, not that good. Shorter, if you move too slow here, it may also be not quite good because you have a noise, well-known noise flow. When you keep having slower movement, they are not that good. We are good. But you will say this is specifying a model. How about model free? Because MPT, if you are comparing with it, by the way, if you specify a model, that's actually good. Maybe that's somewhat related to calibration because directly relate data to model. Estimating the model is actually one point. So you may want to specify a model for some scenario. Of course, some system, you don't know the model. Let me just show this reason result. This is non-parametric, model free. So for this, these are the blue ones. For all this. This you don't assume a model. You use this. Then you may ask me, how do you do this optimization? That proves you indeed. We start with this optimization. We haven't published this result. This is high dimension, 1,000 or 500 time plan. How do you do this 500? We actually do this. This is a smooth. If you look at here, we just reconstruct it in the log space by assuming around like 6 point. And then you only optimize these 6 point. The rest you reconstruct it by Gaussian process. It's very fast. And then that's what we do, and the result pretty good. And then compare with our non-initial approach, we have a package before we publish a PRE paper. That's do something else, but not initial. They are actually good, but actually, you see at the region like this, they just truncate. They cannot analyze. This we plot in the log scale. They actually like only can analyze 1/5. All those challenging information, no statistic cannot do it. So this you can do it because it's maximum marginal IQ estimator. Asymptotically optimal, naturally weight thing. So we don't need to select or choose any wave vector. Okay, yes.
Can you give an intuition for why the average delta x squared was always overestimated in the other models, I suppose?
Oh yeah.
Why is it always over?
Good question. I need to think. It could be a coincidence, could be some. Let me just, maybe I have to guess. I need to go back to check. Because look, they use many large frequency. We didn't select, we use all. Like us, we also use all Q. We select all Q. Then many are like, so when you have very little noise, this A is almost zero. It's just hard to estimate. And then if you just weigh them equally, and who knows what you shouldn't weigh them equally. Right? Yeah, if you directly start from this way, it may not be that good. And the model selection is still also good. You can use, for example, this we use predictive variance. If you choose model FBN, choose OU, you can select it like this OU, the OU, like this, that select OU FBN. The FBN have the smallest predictive error. For BN, it's a special case of OU and FBN. So they are subcase and they are all the same. So when they are all the same, you select smaller model with less parameter. So this is BN. So you can do model selection. And you can also analyze anisotropic, like this is anisotropic processes. That's what we do. For MPT, it's even harder because if you move very fast in one direction, very slow in one direction, if you just search a radius, it's hard to define what radius, right? So, but anyway, this you don't need to define all this. And then some real experiment just quickly, these are optically dense, even smaller than diffraction limit. So particle size is, for example, like this is 100 nanometer and each pixel is around 300 nanometer. So it's smaller than diffraction limit. We can push the limit. For MPT, it's too small and too many particles. You see it's underestimation. This is literature value. We are actually close to literature value, and all interval coverage cover that. And then this is something very interesting, and because this is a hydrogel. Hydrogel is very important material. It encapsulates the cell, so people use. So it's in surrounding environment of cell, and determine the gelling point is one critical goal. Conventional thing people will do, they first tune the parameter, track this particle. So for each of this is one video, they find out MPT, and then they have an experimental list. In theory, it can be collapsed or superposition into two master curves. One is pre-gel, one is post-gel. And then they just start a PPT sheet, and then they do it by eye, still, by hand, by eye, and then they just shift this curve and then make the a line. And then they will record how much they shift. And then they look at this asymptote, this one is the gelling point. That's defined as the largest change. And then we just use our model and define OU because it's pretty confined at the end. And Ohan-Wurldenberg process, we look at the largest change. So it's a row parameter, largest change. We fit a logistic curve and largest change in inflection point. The history value is around 44, so both are similar. So this is automated. You just need to click. For processing one video is similar to MPT in our algorithm. For DDN, originally it take 1 to 2 hours. We improve it. For this, we take 1 to 2 minutes for one video in my computer. And then you don't need to tune. Okay, and then anisotropy, let me just skip. Let me say similar. And people actually like to see it's not easy to make this type of material. They are anisotropy in different size. 1 hour almost. But let me say the second time, the most important thing I will say a few times. So this is, let me just say, we are, so that's the principle. We build a probabilistic model of the untransformed data, okay? And I show the equivalence of physics estimator to the statistical estimator of this generated model. We derive a more efficient estimator by marginalizing our Z, the quantity, and then the physics model can be encoded in Z, that random vector processes. And then we derive maximum marginal IQ estimator. We use fast algorithm with no approximation, to almost no approximation. If you use all Q, right, that's no approximation. So, yes.
So all this is assuming that your data are sort of uniform, like this read, there's no clumpiness in the cells or anything that is. And if there is, what happens?
There are many. That's a very good question. In microscopy, if your particle aggregates, then any method cannot work. And actually, they can have two types of particle they can model in F. So anything new, you change F, that correlation. You can still, like, if you have a drift you want to remove, you can change F. Now I give you a model. You can add this into the model now. See, that's the thing I want to add. Okay, once you find out this generating model, you can keep adding that pieces you think that's in your data.
So how do you add clumpiness?
What's clumpiness?
Clumpiness, groupings of particles or cells.
Yeah, so grouping maybe make them, they have different, let's say grouping may affect their dynamics. They may affect how they move. Then you can derive, they may move as different processes. They may induce different that intermediate scattering function, that correlation. Then we need some physics first, seeing how they model this, and then derive F. I myself actually have doing some of this, deriving different process, how to add different pieces, states, because these we are generalizing into different type of thing. Yeah.
I mean, so in the model, but if you're trying to do this non-parametric thing.
Yeah.
Yeah. Is it, for example,
okay,
can you say that here we got some data set, we analyze it, say that it is not
not
the right model?
Oh, that's a good question. So you are talking about if model are not, that's actually a very good question. So that's another thing I want to highlight. So people now these days show for this type of approach, they look at this D image structure function and show they fit, but they are very different scale, which wave vector you are looking at, right? So we do this EDA on the original scale. So we do a model and predicted mean of that model and look at the original image to see reconstructed by the model in terms of forecast next time point, whether that fit the next time point. That's what we do, original one, not the transform one, because transform have very different from the amplitude. So that's why I say if you want to do EDA and see how it fit, do at the original one, reconstruct by model on the initial data. That's what
I actually want to ask you, I think these 2 points you make here. I understand second pretty well because marginalization usually makes it more efficient. The first one, you talk about transform data, you're talking about, this is not a general principle, are you talking about transfer from the spatial domain to the frequency domain, or what do you mean
Good
by the
question.
transform in general?
Very good question. This is so good question. In this case, this transform is Fourier transform, and then get all the thing to the statistic like DQT, and then you build the physics, build a loss function for that DQT. That I call transform. Many step of transformation. And in physics, this is not uncommon. Many things you need to do multi-step, transform and fit. But if you do that, and if you think about the noise and uncertainty of that data set, they can be correlated for that DQT, right? Can be very different. That at that time to define loss function is not that easy. On the original one, the image, if you build this like L2 loss and correlation, you know the model assumption. So from the original data, you kind of know the model assumption better. And then you can, so this original, I will say, is you know what you are assuming from that loss function. So that's why I want to say it's original data. Yeah.
Are you saying that the original data you have a better understanding from the scientific knowledge?
From the noise part.
For noise part. And I'm still not clear what do you mean by transform in general. I understand when you do Fourier transform or the Waves transform. So yeah, are you saying that these transformations help you to do modeling or help you to do computation?
Yeah, because look, physics derive theory, they don't put a noise there, right?
Yeah.
And then we derive this theory, and then at a certain point, it may reduce data, it may have a technique, and then you can fit. At that point, noise is already forgotten. But in reality, you have equipment, you have all this noise, and you transform it, how that noise distributed, like that B term, just really hard to. So in reality, we really need to think about how this noise is transformed as well. But if you start to do that one, that could be hard. Fitting variogram, directly weight, people try to weigh, could be hard. Then I say, no, why don't we just start from the original data and see what the model assumption there? So that's what I think.
Okay, so you're saying the original data, whatever you mean by that, is because it comes, for example, comes with measured data.
Yes.
Right?
Yes.
So now the physics model themselves was built on assuming there's no measurement.
Yes.
Right, okay. So now, so before your work, what people do, they transfer the data with the noise into another form, then denoise them.
Yeah, this is a very good question. I want to answer. I cannot say they don't deal with noise. You see, they have B part. They have a B part. B is a random noise. They know it's non-zero because it's a variogram. It's a positive mean.
Right.
They do it. They try to do it. They try many ways. But you know that statistic is not easy to do. So they do lots of work. Let me acknowledge. Some are beautiful, and they define many good estimator of A and B. But at the end, you wait for your information. It's not easy. That's
right, because there's lots of knowledge. But tell us then what made it easier for you, like your approach, why that's easier. Like usually you deal with the measurement errors, right?
Yeah. So why is easy? Because if you look at the original data, then you think you want to fit that one. You can kind of think you build a model to fit you want to reconstruct the process on the original one, the process. That one is, or let me say, if you really have a model, all the propagating, writing down the noise, do that, that's fine, but can you? That's a question. So, right.
As a statistician, we obviously say if we understand the physics model, we also understand how the measurement error comes, any errors. It gives us a way to write down the likelihood, right? At least
Yes.
in principle, whatever like volume write down, and then you can propagate from there.
Yes.
Follow all the principles, you do that.
Yes.
And is that what you meant by you do the uncertainty quantification from the very beginning? You basically say, go to the first principle, build the model, don't process the data, like if it's the same, then later because the thing's already, you lost it.
Yeah.
Is that what
Yes,
you
it's that's what I'm saying. I was want to from the beginning and start from there and think about what the data start to process. It's also like some spectroscopy, and I asked some climate scientists, how your data acquire, how do you I probably don't have time, but next also have this many step of processing. How do you get that standard deviation give me? Are they independent of that? Right? So that's what
So in a way, what you're saying is that because in practice, people tend to do some pre-processing of the data. Then they do model on that.
Yes.
But you're saying, don't do the pre-processing. You do the model directly from the very beginning. Pre-processing becomes part of the model. Right?
Yeah, that's something. The pre-processing is so important. It inspires, it's useful. Let me say reduce it useful, but we have to think from the beginning what this processing affect the uncertainty, weighting, estimation, etc. That's what. They are useful. Actually, many these laws, you will see a few generalization. They inspire a more efficient estimator, and we will know the assumption better for many approaches. So anyway, marginalization for statistician is maybe review. I won't say this is iconic feature of Bayesian analysis. So you basically integrate all the randomness, and then at least start from definitely. So they basically say if you think your measurement is changeable, if you have a random variable with probability distribution, that your density follow this way. So these people use it as a justification base because if your data is changeable, you implicitly assume a base model with a prior pi theta and a conditional model. And then in many marginalization and many applications like Bayesian model averaging, model selection, and you define some objective prior from the aiUQ, you could induce an improper posterior, but if you integrate out the parameter random quantity, define the feature information matrix of that marginal aiUQ, you can make a posterior proper. In machine learning, they are becoming also more and more realized. You can propagate uncertainty and more overfit. Okay, so just give you a few tools. I don't know how far I will go. For PCA, for example, principal component analysis, there's a paper called PPCA, Probability PCA in 1999 by Tiffany and Bishop in the CHASC paper. They basically show that the PCA, the latent factor loading matrix, is the linear subspace is equivalent to such latent factor model with this assumption, with Z is independent, and suppose you reduce to D dimension, and then E is a noise. So everything independent, you estimate A by integrating out Z, and then that's linear subspace exactly the same as PCA, and then you can think this is a generating model of PCA. And then in our and for time series and all this, because these assume independence, how about time series, right? Spatial processes. We basically say, if you have this temporal correlation, if you model them by some Gaussian process or time series dynamic linear model, you can still do this. We sort of derive the closed form estimator, the maximum marginal likelihood estimator of A, integrating out all these Z factor processes for any theta. So if they are the same, we have a closed form. If they are not the same, we are having, well, anyway, let me try to hide this flowing control. So I have a certain way that allow you to fast computing. You have an assumption that's adopted in quite a few latent factor model. Anyway, that's one data generating model for both things. And then let me talk about next Kalman filter is also another way of marginalization. So you basically think about continuous or discrete linear state space model written as this way. And then Z is latent factor, can be high dimension. Actually, this Y can also be multi-dimension, but maybe let's focus on 1D. And then Kalman filter, 60 really good work. They basically have an iterative way to integrate out Z by hand. And then from there, you can get the likelihood and also all the predicted distribution in ON. So F and Q are from this F and Q. And then it basically compute the inverse Cholesky times y. That's common filtering, computing like who. The remark, we have a paper and have some other application. Actually, is z is integral, and the computation is on, not n cubic. N is number of time point. And I write is common Bayesian, or perhaps just he think about Bayesian because z is marginalized. And then can I ask, this is a common filter. Have you ever heard anything like inverse common filter? No, because you know Fourier, you have inverse Fourier, right? So common filter actually compute this L inverse times Y, this iteratively. In our very recent paper, we actually compute L times Y and LT times Y in linear order for inverse common filter, then put it in our magical amount is put in archive. And that's quite a few applications. I have large vector autoregressive model. You actually can compute a matrix multiplication times Y very fast. And then they can also compute make it colorful, like it's making it correlated. It's like common is like whitened in computing like and also computing some interaction kernel of cell. That's an application. But anyway, that's something I don't have time to talk. And then this DMD is also another widely used tool. It's only change a letter, but it's a completely different tool in dynamical system. It's related to something called Kuhlmann operator. Also used widely in robotics, in other application. So this DMD is a sort of like discretization estimate of a Kuhlmann operator. So it basically computes something like this. If you think about, you have a large spatial temporal process, you just have n is a time, you basically look at the difference between time point, you reconstruct it by a matrix. This is also related to something vector autoregressive model and gradual causality. They actually, but they are not connected yet. These are really high dimension can be. And then basically they are estimating this A, which is their algorithm, computing something like this. If you look at this in statistics, you may already have the idea what is a data generating model. Interestingly, you may think they are independent. You have a Gaussian reconstructed, right? This is what I mean large. So at the beginning, we indeed very quickly derive is independent is I. You can write down this as I, as a certain sigma 0 or something, sigma. But it's actually any sigma ipsilon. They all work. We can show it. That's a general. And actually, the better than I is more flexible. So quantifying uncertainty is actually better. So that's what I mean large. You want a larger model that can still estimate by data. And because of this, you can actually get a predicted distribution for DMD. But DMD, we also have some following our work. One thing is noise is not modeled. If you see the previous one, I define the noise. For the PPCA, GPPCA, common filter, they typically all define noise. By noise, I don't only mean measurement noise. It can be measurement noise. It can also be model discrepancy, either one of this. You want a noise, but this does not have a noise. With a noise, we actually have a good algorithm and quite some trick. There's a way we estimate by EM and fast linear, this kind of thing. But this is not a simple problem because A is quite large. There's something, yeah. Anyway, and then the process is also not differentiable, right? This induced process, now when you write down, you know what they are doing. This is induce a process like OU, but a high dimensional version is not differentiable. And then it's like mature and other thing that you can build as nonlinear operator. We have a paper revision submitted to Physical D about using some nonlinear operator about that. But anyway, how much I can talk?
We have about 15 minutes, so
Okay. Good, thanks. Then let me introduce something completely different, but still imaging and still time series. So this is real data again. It's on Volcano. So 2018, well, the data I'm talking about, two types of data. This data is 2018. I work with Kyle Anderson, first author. We still are writing paper, working on paper last week and something else. So this is a paper on science. It's about 18. There's actually an eruption at Kilauea that burned hundreds of houses, and then we have the data on that thing. So it's a physical process. It's like this. So the chamber, they don't know the chamber where it is. They don't know how fast it goes, how large it is, and then there are physical eruption here, and the houses are here. And then the measurement data, so we want to know how the process is. We want to know where the location of chamber, how large, the pressure change, etc. And we want to use the data to add a constraint. What data is? This is ground deformation. This is very sensible. We can measure actually centimeter, but for this event, it's meter scale change. I'll show you a video. So this is color. You show the change of the ground change. That how much ground change. If for no eruption, it's like magma going into that, you will inflate the surface. More magma inflate the surface. So that people proctoring the volcano by this, and also the earthquake, etc. And these are the continuous time, the GPS, and then there's some tilt data. It's sort of like the GPS is 3D, tilt is 2D, measuring certain rotation. When I was there, basically what I do for this paper is mostly they just ask me, my model is too slow. We're gonna do Bayesian inversion. Actually, this paper is Bayesian. They have all this data, have a Bayesian model, use posterior sampling, and to calibrate and to estimate the parameter, which is like where the chamber is, etc. But there's a model, there's a link, physical model that's solved by is the PDE. Is the finite element method. It take a second, not that bad, seconds type of, not that big. But you do 100,000 MCMC, they just don't work. My work is made them fast. The paper is basically we accelerated, simulating this like 10 to the 5th run only take a second in our package, and then it can be it's very accurate. So it's originally R. Because of you asked me, I changed the important part to MATLAB. That's 2019. I basically stay 2 weeks in a hotel, USGS, and they say this is something emergent. We need to get this paper done, and then I stay with them, and then they pay my visit, and then I help them implement this. And then my student recently implemented Python. So this what is the important piece. Of course, they have robustness estimations, but it can do something like this. It's F can be a really high dimensional function, can be space, and then X is not that large, but it can be large if you use Euclidean distance. Can be also high dimensional. So this can be very fast. It's linear to the can be the first spatial point. So that's a package. So anyway, so it's also widely used for some non-financial, but this paper is I don't know them. Yeah.
Computer here, are they trying to use
This computer model simulation, that's what I did. So, but what they did is using this to estimate the change, ground change.
And the purpose for that is for understanding of future prediction of
understanding the physics, inverse that where the chamber is, how much volcano, the magma does it map with the how much the volcano goes.
And the what was the original data?
Original data is this image. And then the time series.
Original data are just image.
Well, tell me. This is a good question. It's also process image. This actually interfere. That the second part I introduced more is the interference of radar wave. So this is not the image. It's after many steps of transformation, give you the change of ground. It's from satellite. They put the wave and then look at the interference between two waves. It's about 2 waves or something. Actually, that technique I'm not that familiar with, to be honest. But it's a kind of way.
Is the satellite image during the eruption, or this is over time? Like
during the eruption for this data, but I'm not showing too much on this work. But later we will see how the time span. Usually you need to, like a month, you see a little change. 3 months. This is by data. Or let me play a video. Good question. I almost forgot. Thank you for that video. Sorry for reminding me to play that video. Sometimes I just cannot. You will see what do I mean by that. It's pretty. Let me play this video. Okay, let me play this video and just okay here. So that's the data. You have this eruption and then it's crater. That's the first few days. Each is a day image, and then you see this flowing, and then when you see this going down, this thing going down, this thing going down. Look, going down, going down, going down, going down, going down.
I see.
This is drastically changed and it's
But
imaged by the
this, when it goes down is what's the time span? Is real time?
time, real time day. Each image is 1 day.
So it's going down every day by a little bit. It's not a crash.
Almost crash because that's the magma from this 2 kilometer else. So it's basically magma going to somewhere else. And because of loss of magma, this ground go down.
I see.
And then they can have build a model and then link this what's where it is and but usually centimeter change, if you know your reduction by months, this is like this scale is huge. That give a kind of a lot of measurement that we will never have, sure. But indeed, it's a lot of thing there.
What's the precision of the measurements?
Oh, that's a good question. That one actually, for that one, they in the centimeter, you can sense like 3 centimeter, and then the standard deviation is like 5% or something like that. It's quite a good. But that's what I mean by imperfect data. Everything is perfect, they can do that, but they have atmospheric error correlated, right? All this, and then calibration is a big problem.
Do they also take into account variations in the density of the Earth's crust when the magma moves away?
Yes, there are this Poisson ratio, rock property.
Which would make the satellite change orbit.
Hold on, you are talking about the underneath the physical process, right? You are talking.
I mean, I'm basically asking about the measurement and what sort of systematic errors there might be in addition to just the measurement.
That's a good question. So there are a few parts. There are this the equipment error. There are also this atmospheric error. There are other things. But
they're measuring the height from satellites. Right?
yes, height from satellites.
So the question is that satellites, the orbits of satellites depend on local density of the Earth's crust.
Yeah.
So if the density changes, for instance, huge volumes of magma move.
Oh.
It will change the orbit a bit.
I think they look at the ground. Where's the altitude of that ground? They basically look at
that also depends on they know where the satellite is.
Yes, they know the where the satellite.
And if the gravity of the Earth changes underneath,
that
cause centimeter.
Oh, I don't know. That's actually a good question. I don't know. This is, I think these are you. I'm not sure my collaborator also know this detail. Yeah, but yeah, good question. Thanks. Yeah. Anyway, let me maybe just. I don't know which part you want me to go. The first part is actually from statistics, and it's a statistical process. I can quickly let you know what this is doing. So the first part is on imperfect model, but data is kind of perfect. So people typically model, if your model is not perfect, you add some nonlinear like Gaussian process to enhance it. That's a conventional way, and by Antonio Hagen and many other people follow. It's just what if your model are not that good, can you improve it? They find it if you add it in terms of predictions, forecast better than just using your physics model. But then you will create something identifiable problem, the theta and delta. You see, delta is so flexible, it can dominate. So that's a big problem. And then the people, let me just show you one slide. We can show for simple like a model, even without the measurement error noise. And if your model is just a mean, if you assume this correlation, if you use in-field data asymptotic, like in-field you have more and more close, and you actually will see something like this. You have an infinite amount of data, even the maximum likelihood estimator, the mean square error won't go down. It's kept, so it not decreased to 0. And as a statistician, you will first be very surprised. But it's sort of like not the correlation is bounded. So that is sort of studying spatial statistics. But that's one problem. In real what data is not come from Gaussian process, you will see a difference between two models. When you have more and more correlated in terms of likelihood, you will have a smaller and smaller difference of two likelihood. So the same difference of the mean, but if you have more correlated means they are getting closer and closer in the likelihood space. So that's a problem. And then the estimated model can be deviated from data. So in terms of it, so that's a problem. And then there are people quite a representative paper from Jeff Wu's group from Georgia Tech and his student faculty at Texas A&M and Raymond Wang at no, Raymond, actually no, they both are in Texas A&M, these two people, but they do this two-step. Two-step first, the first two-step is they just estimate the reality without a computer model, they fit, and then they estimate theta using some L2 minimization. The second LS is you first estimate the theta by some L2 by some this loss, and then you do nonlinear regression on the residual. The first part is if you don't use your model, that can you improve prediction, right? In some complex problem that may not be that good. The second, residual is harder actually. If you directly do with residual, you want to smooth it, residual jump up and down. But this is a really good approach. It actually inspired me to do something what I did here. So this is a new kind of, we construct a process, how to do Bayesian. We basically build this conditional one. This condition is on random L2 loss, and we gonna build a new one to scale it. So this this Z is L2 loss, and then you sort of try to scale it. Scale means, for example, default use exponential, and then scale it means what? Because the thing is, when you correlate it, you have really lots of mass on large L2. In your prior, you probably don't want it. So I basically built this to scale it. This is CHASC. When I was at Johns Hopkins, this is a student, no one, and we can show any Gaussian process a special case of CHASC with number Z equal to 0, and there are default choices for number Z, and there are many good property. We can show, for example, this reconstructing this thing. Maybe make it. Yeah, so this we can show in terms of orthogonal reconstruction how this SCAF, this induced kernel related to original one. So any kernel you induce it. So it's sort of overstatement. We build a new process, but if you think all Gaussian process people use with this kernels like this for any of this, we double the size. For any kernel, we have a new scale kernel. But you have we can study the eigenvalue, what they are. They sort of shrink the eigenvalue, and then you can plot it. You have something like this. Let me just quickly maybe go through. We can also show the maximum likelihood estimator is equivalent to this like kernel ridge regression, different than the regular like Gaussian process. Kernel ridge regression is you have this number Z. Both of them, they are independent term. And just quickly showing you all this convergence result. We have all this converge to the reality, converge to the mean in terms of L2 loss. And it's not so easy to prove because of some unboundedness of number Z, but we do have this convergence result. Let me maybe just quickly, and a theoretical bound match the numerical bound. And actually for this, it's we don't sample Z, that's the thing. We can integrate out by hand again, that induce a new kernel. We can discretize it and then induce a new kernel. So anything that they are this good computation, and then there's a default choice of something. But let me, because of modular distribution, we all have it. Let me just quickly show you what results are. For example, this is compared with two-step prediction. If you use a model, you can improve it. Let me tell you maybe what next part is. These are the processing I'm doing. So they interfere with this wave, and then they map to this. And then because there are many pixels, they sometimes need to do this so-called core tree to reduce it, that capture the large change. But that's the processing. But this is sort of, if you look at here, this part, this is atmospheric error. This is well known, is a big part, and then there are methods to do it, but this will basically model it out by this. We just add another model to this, and then they usually just stack it. They just look at the average, and then we actually discuss what's the difference when it is sufficient, when it's not. Actually, for most cases, it's not sufficient statistics. So we have some theorem. Basically, for example, one I summarize here. If you assume that model, right, without measurement error, the correlated case, but with only a shared delta, and then if you average, that's what they do, like stacking. You actually can show two likelihood they are related. And then if the sigma 0 is known, then they are equivalent. You can reduce the computation time a lot if you stack. But if you are not known, then the individual data is much better for estimating the sigma 0. And then this is a package. We have talked about two packages now also, maybe three. But this is also R. We have this package. We have different like multi sources, one sources, and different function. And then this is just showing you we can for this model. If you simulate from it, we can identify the truths. And if you stack it, it's not that good compared to ours. And some of this probably I would just skip because time is up. Let me stop some results. So this is the third time I talk about this. So in China, there's whole saying called important thing 3 times, so people remember. But if you ever watch like Big Bang Theory, when Sheldon Cooper knocked at the Penny's door, you would have it 3 times, penny, please, right? So say 3 times. So this is the third time. That's the sort of general principle we think that we do. And then data factor model, actually a general model for many physics processes, imaging function. Physics model can be encoded in correlation. And fast exact approaches, like this, like we do more like common filter, but now we learn some Shu and also fast Fourier, and then can be reduced without approximation, reduce computation, and then thank all the student and then co-author. They are all actually from different departments, mechanical and physics, winning from UCI and from the ground. And one more important thing to show if you are a master student undergrad, please apply to, if you're interested, check our page. And if they are good to PhD graduate, like Alex Franks, yeah, let me know. We have a position. Okay, thank you.
Any particular suggestions on how this can be used for strong stat problems? Do we have these dynamic situations?
So the question is, do we have this dynamic situation? I forgot to repeat the question. Is it useful or useless at all?
Yeah, I mean, what you said about can you go back one slide where you had this thing about the, oh no, sorry, the summary.
Yeah.
Where you can have the
I just want people to hear what you say. Oh, there are hands.
Anyway, where you said that the physics model could be encoded in the correlations, right?
Yes. Dynamics.
So that,
yes.
I think that is something that we have not explored, I believe, Joey. That might be useful to do. I mean, we have tried to do instrument models encoded as PCA variations, and atomic physics encoded as PCA variations. This is something we have not explored. It's worth checking.
But statistically, you're basically using a latent model to do the PCA.
With a prior physics. So that constrains the space. The generated model is not independent anymore.
Right. Okay. And then your contribution is other than modeling is really trying to do computational fast.
Our contribution is linked to physics and stats. This is build a data generating model. They don't know before. Actually,
but so the computation, that the software itself,
that one is not
there.
But you need to code it. You need to sort of get the root all this. But it's not that one is not.
Jeff Scarborough has.
Jeff has a question. There's a question.
Go ahead, Jeff. You don't have it.
Thanks. Very interesting talk. Is it convenient to go back to your slides and show the very first?
Sure. Let me see. Let me know when to start. Very first.
But it'd help me if you could share it on Zoom also. But
I didn't share on Zoom. Okay. Let me share.
I made it without. But basically, you're finding for was sort of like the distance. You didn't say explicitly a distance measure between the data and the model, but there was sort of implied.
Okay, sorry. So sorry, I'm still trying to share. Let me share. Sure. Okay, good. Yeah. So yes.
The very first slide.
Yes.
Yes. So you call it a loss, but anyway, I'm interested in a class of problems that's different from this, but I can't really tell whether it's a special case or a generalization. And that is where you have a model that essentially can be fit to the data exactly with various parameters, but those parameters are not determined. It's kind of like an over or underdetermined problem or an ill-posed problem in a way. So the loss is usually defined. The distance between the data and the model would be identically zero for essentially any value of the parameters. An example is a simple example in time series analysis is fitting autoregressive models where if the innovation is considered a unknown, you can fit any data exactly with the model. So you have to impose some other physical constraint, which isn't in the form of the distance between the data and the model. Is that class of problem something that fits into your setting here, or is that outside of the scope of what you're talking about?
Yeah, this is a really nice question. So the question, if it's over parameterized, then you need some constraint, like identifiability issue is sort of like related to the second one. You need some like prior to constrain it. It also fit into this paradigm. So this paradigm, it's more about whether how to model the noise in the transform data, not transform. So even at the end, it's over parameterized. You want to fit. You might also need to think what the noise is, right? When you include those constraints, right?
Yes.
You may still need to think about the noise. But if in some cases you just have number of equation, number of parameter, if that's unique, yeah, you still need to think whether you want to wait. Again, let me just say this. So if you think about the transform, even you want to solve that equation, but is that certain transformation makes certain transform quantity more important than the other? That's what I'm saying. Then you might need to think about the beginning, what this is doing. But yes, I think it is still in this case. But that's a problem I haven't done, that you reduce to a certain point that you cannot estimate the parameter, right? Constraint.
Yeah, okay. I don't think of it in terms of a transform, but I guess that's similar. It's just different language from what I have in mind. I mean, basically you just have a bunch of free parameters and any values of the parameters fit the data exactly.
Uh-huh.
It's crazy, but it happens in, I think, a lot of problems. So you need to impose some other, you have to invent a new metric is what it amounts to, that isn't just a simple comparison of the data and the model. But anyway, thanks for the insight. I appreciate it.
Thanks a lot for the question.
All right, any other questions?
Okay, thanks.
We have well over time. Thank you. It was a very nice, very interesting talk. So
Thank you very much. And for now, you earn a free lunch.
Thank you. Okay, thank you.
Thank you.